Okay, so this problem we're going to work another second law problem with an open system. This time our open system is a heat exchanger. Alright, so let's start off, read the problem statement. Air in a large building is kept warm by heating it with steam in a heat exchanger as shown below. So we're given the figure. Mostly it just labels we have water on one side and air on the other side of the heat exchanger. Saturated water vapor enters at 35 Celsius at a rate of 10,000 kilograms per hour and leaves the saturated liquid at 32 Celsius. Air at 1 atmosphere enters at 20 degrees Celsius and leaves at 30 degrees Celsius at the same pressure. Determine the rate of entropy generation in the heat exchanger. Alright, so let's start off, just set the problem up. Our system here, we have air, which is an idle gas, and water, which is a phase changer, in a heat exchanger, where a heat exchanger is an open system. For the conditions, we have a steady process, and we apply the heat exchanger conditions, right? Heat exchanger conditions, Q dot, W dot, and kinetic energy effect, potential energy effect, those types of things are negligible. For the properties, first of all, we're given inlet properties for the water. So let's start off there. First thing it says, we have saturated water vapor at the entrance. So X1, the inlet for water, is 1. As saturated vapor. The inlet temperature of the water is 35 degrees Celsius. And the mass flow rate at the entrance, at the water entrance, is 10,000 kilograms per hour. We would want to take that number and convert it to kilograms per second. So to do that, we would divide by 3,600. That gives us a mass flow rate. Calculate it here real quick. Let's clear out everything from the last problem. M1 is equal to 10,000 divided by 3,600. So about 2.78 kilograms per second. And then the water leaves as a saturated liquid. So the quality at the exit for the water, X2, is 0. And last thing, the water leaves at a temperature of 32 Celsius. So that's it for the water. For the air, we have air at 1 atmosphere at its entrance, which is 3. So we would probably want to take that atmosphere and convert the atmosphere to kilopascal. So in kilopascal we can use 101.3 kilopascal. Roughly 1 bar. The entrance temperature for the air is 20 Celsius, so T3 is 20 degrees Celsius or 293 Kelvin. The exit temperature for the air is 30 Celsius, so T4 is 30 degrees Celsius or 303 Kelvin. And then lastly, the air leaves at the same pressure that it enters at, so P4 is equal to P3. Any other information? No, we're not given any other information. Alright, so there's our properties. Now we're ready to go ahead and try to solve. What we're looking for is the rate of entropy generation. So that's capital S gen dot the rate of entropy generation in the heat exchanger. Alright, so this is the heat exchanger problem. What we can do to kind of speed the problem up a little bit is basically look back at some of the examples and the notes that I gave on heat exchangers and just pull out the equations that we find the most useful. So if we look for the mass balance on a heat exchanger as the system, that would be multiple inlet, multiple outlet system. Okay, mass balance, what we end up with for the heat exchanger, we start off and it looks like m dot 1 plus m dot 3, those are the mass flow rates at the exit, or sorry, the inlets. It's equal to the mass flow rates at the exits. Then what we would do is we apply the mass balance for the air and the water separately, and we know that m dot 1 will end up equal m dot 2, m dot 3 will end up equaling m dot 4. So we take that back up in here. The mass balance for the heat exchanger doesn't really tell us anything all that useful. Alright, basically just gives us a true equation. So that's the mass balance for the heat exchanger. The energy balance for the heat exchanger, we would have Q dot minus W dot is equal to summation out M dot times H plus KE plus PE minus summation in M dot times H plus KE plus PE. So for the heat exchanger as a system, we can cancel out Q, we can cancel out W, kinetic and potential energy, and we get a mass flow rate times enthalpy balance. So we have mass flow rate at the end, 1, and at the out, go ahead and write this the original way. So that would be our energy balance for the heat exchanger. And then we would do the similar process that we've done before, where we look at the energy balance for the air and energy balance for the water as the system, combine some information. So we also know from the mass balance m dot 1 is equal to m dot 2, m dot 3 is equal to m dot 4. For the energy balance on the heat exchanger, for the air energy balance, we get that the heat transfer to the air, we can say that as 3/4. That's the heat transferred per unit mass to the air is equal to H4 minus H3. Heat transferred to the water is H2 minus H1. Alright, this is Q for the air, this is Q for the water. So if we plug that all back into the grand energy balance equation, first of all we see here m dot 1 and m dot 2, those are the same, so we're going to combine those two terms. We have m dot 1 times H1 minus H2. Then we're going to combine on this side, m dot 4 is the same as m dot 3, so we have H4 minus H3. So this is the typical energy balance equation we get for the heat exchanger as a system. Just look back in your notes, you can find this equation. Also, the example that we worked in chapter 4 for the heat exchanger, this is the resulting equation that we get. Alright, so here we have basically some enthalpies. We have H1 and H2 that we would need to look up for the water. For H4 and H3, right, we don't look up enthalpies for air. We do, right, delta H of the air. We approximate using our constant specific heat analysis. So we approximate delta H of an ideal gas as C sub P, right, times delta T. So we would have T4 minus T3. Alright, all that's doing is taking delta H for an ideal gas is C sub P times delta T. So now looking at this equation, what are our unknowns? Right, we know the mass flow rate of the water, but we need to look up H1 and H2 based on the properties of the water. We can look up specific heat of air based on T4 and T3, and we actually know T4 and T3. So let's start off by just looking up H1 and H2. So let's look at inlet 1, which is water. And we're given, for inlet 1, properties X1 is 1 and T1 is 35. So H1 is going to be, since we have a saturated vapor, it's going to be H sub G at T1. So for the water, we're going to go and look up at T is equal to 35 degrees Celsius. What is H sub G? So we're going to have to get that back up into table A2. And then in A2 we're looking for 35 degrees Celsius. What is the value of H sub G? So here's the 35 row. H sub G, see 2565.3. So there, that takes care of H1. Also, we know that we're going to be using the second law in this problem, so if we wanted to, we can go ahead and look up specific entropy. It should be important at some point when we use the second law. So we can go ahead and get S1 while we're at it, SG at T1. So SG is located 2 columns to the right of HG. We see 8.3531. Alright, so that's state 1, inlet 1. If we look at exit 2 or outlet number 2, again we have water. And our properties at exit 2, we have the temperature is 32 and the quality is 0. So our value of H for a saturated liquid, quality of 0, H sub F at the given temperature. So H sub F at T2, T2 is 32 degrees Celsius. So we're going to have to read here for the 32 degrees Celsius. H sub F, 134.15. And while we're at it, we'll go ahead and get S. So S sub F for 32, 0.4644. Alright, that takes care of the water. We have our properties for the water. Also in this equation, we have almost all the information except for C sub P. So let's try to find C sub P for air. C sub P average at T3 and T4 for air. Alright, C sub P at T3 of the air is 20 degrees Celsius or 293 Kelvin. So we have to get C sub P at 293. Let's go down into our specific heat table. For air, to get C sub P at 293, we're going to have to interpolate here between 250 and 300. Alright, so we can do the interpolation here, might as well. Let's get C sub P at T3, interpolating here 250, 293, and 300. At 250 we saw a value of 1.003, and at 300 we saw a value of 1.005. C sub P at T4. Also going to need to do an interpolation, but this time it's at 303, so we'll be interpolating between 300 and 350. So at 300, 1.005. At 350, 1.008. Alright, let's get our C sub P values here. C sub P at T3 is equal to interpolating 250, 293, 300, 1.003, and 1.005. So that gives us 1.0047. At T4, we have 300, 303, 350, 1.005, 1.008. So we end up with 1.0052. Then we take the average here, and the C sub P value that we're using is average between C sub P3 and C sub P4, 1.005 exactly. Alright, so everything in the energy balance equation except for the mass flow rate of the air is known. So let's go ahead and solve for the mass flow rate of the air. The mass flow rate of the air is going to be mass flow rate of the water times its negative delta H divided by here C sub P times T4 minus T3. Alright, so let's plug this in, get the mass flow rate of the air. So we have m dot 1 times H1. I don't have that in here, so I'm going to get H1. H1 is 2565.3 minus H2 was 134.15, and we're dividing that by C sub P times T3 is 293. Sorry, T4, 303, minus T3, 293. So mass flow rate of the air is going to be 672 kilograms per second. Alright, so we've analyzed the first law and we've found the mass flow rate of the air. Analyzing the second law, which is what we really want to be doing to get the entropy generation rate. Let's now write the second law. We want to use the multiple inlet, multiple outlet open system equation for the second law, which looks like rate of entropy generation is equal to sum out m dot s minus sum in m dot s minus sum of q dot divided by T sub b. So the heat exchanger is a system. There's no transfer between the heat exchanger and the surroundings. All the heat transfer is inside the heat exchanger. So this is just going to be mass flow rate at the outlets, which is mass flow rate 4 and mass flow rate 2 minus mass flow rate at the inlets times S Alright, so we'll have to do some simplification here. We can use the fact that m dot 1 is m dot 3 and m dot 2. Sorry, I got that backwards. M dot 1 is the same as m dot 2. M dot 3 is the same as m dot 4. So we can write entropy generation rate is equal to, we have m dot 4, which is really m dot 3 times S4 minus S3. Plus m dot 2, which is really m dot 1 times S2 minus S1. So here's our equation for the entropy generation rate. So we actually do see that we needed to get m dot 3 in order to calculate the entropy generation rate. We've calculated that. We know mass flow rate of water and we know delta S of the water. So the very last thing would be to get delta S of the ideal gas. So for delta S of an ideal gas, we actually use an equation to calculate delta S of an ideal gas. So here for the second part, delta S of the ideal gas, we can write as, based on, do we know temperature and pressure for the ideal gas, or do we know temperature and specific volume for the ideal gas? We know the pressure, so we want to choose the equation C sub P natural log T4 to T3 minus R natural log P4 to P3. Alright, so that's how we write delta S of an ideal gas. And here we notice one thing, that P3 is equal to P4. So here we have natural log of P4 over P3. If P4 is equal to P3, this would be like the natural log of 1. Natural log of 1 is always 0. So this term actually doesn't even contribute at all. And we end up with S dot gen is m dot 1 times S2 minus S1 plus m dot 3 times C sub P times natural log, write this term down on the next line, T4 to T3. Right? Alright, so that looks good. All of these things are known, and we should just be able to plug this in and get our entropy generation rate. So for est gen, we have mass flow rate 1 times S2 minus S1. I'm going to have to go look up those numbers again. S2 was 0.4644. S1 was 8.3531. Then we have plus mass flow rate 3 times C sub P, same value we've used before, times natural log of T4, 303, divided by T3, 293. So our entropy generation rate is equal to 0.751. What kind of units do we have here? For the mass flow rate, multiply kilograms per second times kilojoule per kilogram Kelvin. So the kilograms cancels out, and we get kilojoule per second times Kelvin. Or actually, we have kilojoule per second Kelvin. Here we have mass flow rate times C sub P. Mass flow rate times C sub P, we would end up with kilograms per second times kilojoule per kilogram Kelvin. So there the kilograms cancel. And then this term is unitless. So again, we have kilojoule per second Kelvin, or a kilojoule per second is a kilowatt. So we end up with a kilowatt per Kelvin. And the entropy generation rate, just like entropy generated per unit mass, or entropy generation, should be a positive number. Otherwise, we've done something wrong, and this device does not satisfy the second law. So this is our entropy generation rate, 0.751 kilowatt per Kelvin. And then to finish up this problem, what we would want to do is sketch out the process on a TS diagram. So let's show the TS diagram for the water first of all. For the water, we need to put in our saturation dome. And for the water, we have a constant pressure line. For T1, we don't actually know the original pressure, P1. We don't know the final pressure, P2, either. But we do know that T1 is 35 degrees Celsius, so we'll mark that here. If I run it across, add a saturated vapor at 35 degrees Celsius. T2 was 32 degrees Celsius, and I had a saturated liquid. So if we put in constant pressure lines here, we can see something interesting. The water actually had to have changed pressure in order to have changed temperature. And we can connect the dots here. We went from 1 to 2. So this would be the TS diagram for the water. For the air, we also can put in some constant pressure lines if we want to. For the air, we know that pressure is 1 atmosphere the entire time. And then the initial temperature of the air was 20. Final temperature of the air was 30. And we follow that constant pressure line up from state 3 at 20 to state 4 at 30 degrees Celsius. Notice something for the air. For air, the delta S is positive, S4 is bigger than S3. Notice for the water, delta S for the water is actually negative. S2 is less than S1 because it's to the left of S1. So in this problem, we applied first law concepts, second law concepts to analyze an open system and determine the rate of entropy generation.